In this lesson, we look at the ttys module. Now, the ttys module is perhaps the most generally useful module from this course. It can be used to read and write data on a serial line, such as a console, and nearly every modern embedded system I worked on had a console like this. It also integrates with the C language standard I/O API for things like printf, and this is very much expected by C developers. The term TTY is an abbreviation for teletype, which is the name of a historical machine used for text communication. At one point, teletypes looked like this. There was a keyboard and a roll of paper where the text was printed. And later, the paper was replaced with an electronic monitor. In Unix and Linux, the device driver to interface to such a machine was named TTY for obvious reasons. Now, traditionally, the communication was over a serial line. But other kinds of communication are possible, such as a USB to serial converter, or even a remote user logging in via the network. So different types of TTY drivers arose. And so the S in TTYS means a serial line. So even though real teletype machines are only found in museums, the term TTY has stuck. A few more things about the ttys module. It's a multi-instance module where you have one instance per UART. And this has an effect on the API, which you will see later on. And the ttys module provides some console commands that we'll also see later on. I want to talk about the standard I/O integration because this is a confusing topic if you aren't very familiar with C and operating systems. Here is the thing. The world of software, for the most part, runs on operating systems. And in bare metal, we don't have one. So when we try to use software designed for use with an operating system, we have to adapt. So an example is printf. C developers really like printf and related functions from the standard I/O API. But these functions depend on another set of APIs known as system calls. System calls are the interface to the kernel, which is the heart of the operating system. Of course, we are bare metal and we don't have a kernel. We see the issue in the file syscalls.c, which was discussed in an earlier lesson, which has the functions for the Linux system calls. As you would expect, these functions in this file mostly don't do anything. I mean, what could they do with no underlying OS? But you can put your own code in them to simulate what Linux would do. For standard I/O, write and read are the key system calls. For example, when printf is called, it does a bunch of stuff, mainly formatting, and eventually it calls write. So in syscalls.c, underscore write and underscore read are the functions we need to implement to actually do something. Now, where did these underscores come from? Hang on just a minute. Fortunately, the underscore write and underscore read function symbols are declared as weak, so they can be overridden. In other words, we don't have to modify the syscalls.c file. We can just create our own underscore write and underscore read functions, and they will take over. So in the ttys module, we have underscore write and underscore read override functions that transfer data to and from the UART. This is the heart of the integration between standard I/O and ttys. We'll see the code in a few minutes. Now about the underscores. A lot of C code, for example the Linux kernel, is full of functions starting with underscore, sometimes with multiple underscores. The underscore usually means a private and maybe a lower level version of a function, and the deeper you go, the more underscores there are. So there is a write function with no underscore that the user will call, but eventually underscore write gets called to do the work. To me, the use of underscores like this is sort of helpful. The name stays the same, but there's just another underscore or two. but it can make the code difficult to read and confusing. But it's something you just have to get used to. Unfortunately, using standard I/O is not all peaches and cream. There is an issue, and that is the standard I/O stream functions allocate memory from the heap. This means they call malloc to allocate memory dynamically. If you don't know about the heap, it is something you need to read up on. It's an important part of the C language. Now, this is not necessarily a problem, but embedded developers get nervous about using the heap, and that is why I put this statement in red. Google the phrase heap fragmentation to understand more about why embedded developers get nervous. MCUs tend to not have a lot of RAM, and the less RAM you have, the more that heap fragmentation can become a problem. However, it might be, notice I underscore the word might, that heap memory is only allocated during initialization for standard I/O and never freed, and this is in our version of libc. That is what I saw based on some simple experiments I did. I set breakpoints on underscore malloc underscore r and underscore free underscore r to see when they are called. And malloc underscore r was only called during initialization of the standard I/O stuff, and underscore free underscore r was never called. Now, ultimately, we would need to look at the details of the libc, or newlib in our case, the libraries, the implementations, and I haven't done that. But using the heap to get memory only during initialization and never freeing it is generally more acceptable in small embedded systems. Why is that? Well, first of all, it's more deterministic. You don't have this ongoing allocation and freeing of memory that can cause fragmentation. And in fact, the heap logic can be trivial if this is the design. The hard part of a heap is dealing with freed memory. I used an MCU library once where you chose what type of heap you wanted. And one option is just this: only allocate, never free. The heap code for that option was trivial. And perhaps most importantly, if you don't free memory, heap fragmentation cannot occur. It's as simple as that. The main thing you need to ensure is that you have enough heap memory to get through initialization for all use cases. So really, in this case, using heap is not that much different from static allocation of memory. The difference, of course, is that with static allocation, you can look at the code or you can look at the linker map file, and it is very clear exactly how much memory is being used. When using the heap, it takes a lot more work because you have to analyze the code. Personally, I think that using the heap in this way in small embedded systems is perfectly okay, but maybe not everyone agrees. And if you work in embedded, you will probably run into this question of using the heap again and again. And as a word of warning, when you use library functions, you might not be aware that the heap is being used. So this is something you always need to think about. I want to talk about using the standard I/O API with ttys. The ttys integration into standard I/O is a minimal one. I didn't view it as a requirement to make it work exactly as if you were programming in Linux. In my opinion, it wasn't worth it. So the information on this slide is especially important if you have done a lot of programming in C on mainstream computers and are familiar with the standard I/O API. So the first difference is that a ttys device is automatically open after the corresponding ttys module is started. With Linux, you usually have to call the open or fopen function before using a device. Another thing is that reads are always non-blocking. This means that when you call a standard I/O function to read data, it won't wait until some data arrives. Blocking is not allowed with the superloop design. So if you do a read and there's no data, you'll get a -1 return code, and the error_no variable will be set to e_would_block, which is the same as e again. This is just telling you there's no data to read and to try again later. In Linux, reads are often blocking by default, and they will wait for data to come in. But in Linux, you can set up a device to be non-blocking, and it will act as I just described. Another thing to know is that UART2 is mapped to be the so-called standard in and standard out device. In C, these devices correspond to the global file streams called std_in and std_out. Functions like printf and fgetC, which don't take a file as an argument, use standard in and standard out by definition. Now, for most standard I/O APIs, you need a file descriptor or a file stream to specify the device. The exceptions to this are the functions I just mentioned that assume standard in and standard out. So anyhow, there is a ttys API to get the file descriptor for a ttys, and there is a ttys API to get the file stream for a ttys. I want to add that the file descriptor and the streams returned by these ttys APIs can be used for both reading and writing to the corresponding UART. So to try to make this a little more clear, here's a code snippet that shows how we use these APIs. As a word of caution, we don't do any error handling in this code. Anyhow, we first declare some variables, a file descriptor, which is an int, and a file stream, which is a pointer to a file. What I first do, just to show you, if you're doing printf, there's nothing extra you need to do. You just can do a printf, and it will go to UART2 because that's standard out. Now let's say we want to write something to UART1. In that case, we call ttys getFD and get the file descriptor for UART1. And then we can use the write statement to print hi. Now if you want to use the standard I/O that uses streams, then we would call ttys getStream for UART6, and then we could do an fprintf of hello world out to UART6. So I threw a lot at you in this slide. If some of this is confusing, you might need to read up a little more on doing I/O and C, focusing on file descriptors and file streams. Now let's look at the header file for the API of the ttys module. Now this module has multiple instances, and there are different ways we can handle multiple instances. In this case, we know in advance how many instances there can be. It's the number of UARTs. So we created this enum that can be used to identify the module. So one of these enum values has to be passed into API functions to identify the module and thus the UART you are using. Now the config structure has just two parameters. If create stream is set to true, then a standard I/O stream is created for the UART, which allows you to use the so-called stream I/O APIs like fprintf. Creating the stream does use some heap memory, which is why it is an option. The other parameter is used to determine if a carriage return is automatically sent after a new line. This is normally wanted for terminals, like for a console. It is normally not wanted if you are sending raw data. By the way, the default for both of these parameters is true. Now we see the core APIs, and notice there is no ttys_run. This module pretty much operates based on the interrupt handler. And then there are these other APIs, and these first two are fundamental to the module as they allow you to read and write data to the UART. If you want, you can call these directly. If you use standard I/O, then the standard I/O API integration uses these module APIs. And then finally, there are these two functions that I discussed earlier to get the file descriptor or the file stream for a ttys module. Normally you will call these if you're going to use the standard I/O API. It sort of takes the place of doing an open or an fopen. Now let's look into the design of the ttys module. I first looked at doing this with the HAL library, and I was able to quickly get something together that mostly worked, but it would drop characters if they came in too fast. I think I could have made it work reliably with HAL, but perhaps not so cleanly. I think I would have had to look too deeply into the HAL implementation. So I moved to use LL, which is what I wanted to do long term anyhow. Now the design of drivers like this often involve having circular buffers that hold data waiting to be transmitted or incoming data waiting to be processed. In this case, we have a pair of buffers, one for transmit data and one for receive data. There is a pair of buffers for each UART. So in my design, each circular buffer has a get index and a put index. The put index is the location where a character will next be put, or in other words, written. After the character is written, the put index is incremented. And the get index is the location where a character will next be gotten, or in other words, read. After the character is read, the get index is incremented. When an index is incremented and goes beyond the end of the buffer, it is set back to 0. This is what makes the buffer circular. When the put index and the get index are the same, the buffer is empty. So we can see that is the case for this TX buffer. Now we can see that the RX buffer contains 2 characters. The next character to get is an X, and then there is a T. After the T is gotten, the get index will equal the put index and the buffer will be empty. When putting a character, if incrementing the put index will make it equal to the get index, it means the buffer is full. You can't allow that put index to equal the get index or it will appear to be empty. So you can't put that character. So in that case, the character is dropped, and we call that overrun. In this slide, the yellow color is used for things that transmit characters out to the UART. And the green color is used for things that receive characters from the UART. And then these blue things are things that handle both sides. So to the left of the buffers, we see these interrupt handlers. And these are the 3 interrupt handlers for the 3 UARTs. Each of these handlers just call a common interrupt handler function, ttys_interrupt, passing it the module instance ID. So the UART has several possible interrupt conditions. The important ones for this code are interrupting when the UART has received a character and interrupting when the UART is ready to transmit the next character. So if the UART has received a character, the interrupt handler will read the character from the UART and it will put it in the RX buffer and increment the put index. If the RX buffer is full, then the character is dropped and this is called overrun. When the UART interrupts and says it is ready to transmit the next character, a character is read from the TX buffer and then written into the UART. Now, what if the buffer is empty like it is here? Then the interrupt type is disabled until a character is added to the TX buffer. If you don't disable that interrupt type, you'll just get it occurring again and again. On the other side of the buffers, we see 3 levels of functions that transmit and receive data. At the lowest level, the ttys putC and getC functions actually put the data into and out of the circular buffers. The next level is the system call functions in syscalls.c that we overrode. They call the ttys module functions to transmit and receive data. And then the top level is the C language standard IO API functions. These functions ultimately call _write and _read to transmit and receive data. There are a lot of functions in the standard IO library, and just some common ones are shown here. There is an important thing to remember when working with code where an interrupt handler is involved, as is the case for this module. You have to be careful with variables that can be modified both by the interrupt level code and the base level code over here. In this project, base level code is the code run from the super loop. Now, the ideal case is that the two levels never modify any common variables at all. Now, with the circular buffers, we don't have a problem. Take the tx buffer. Only base level code modifies the put index, and only interrupt level code modifies the get index. Now, I am making one assumption here, and that is that the interrupt handler does not call ttys putc or ttys getc. If you do have variables that are modified by both levels, then a common solution is to disable interrupts when modifying the variables from the base level. This issue is probably the biggest source of bugs when using interrupts. You always have to have in your mind that an interrupt may occur at any point within your base level code, and you have to imagine what that interrupt handler might do. I still remember a problem like this on my very first embedded project at my first job. I was using assembly language, and there was a bug where if an interrupt occurred precisely between two particular lines of code, that is, two machine language instructions, it would cause a problem. This happened very rarely, and so it took me a while to find it, and of course I still remember that. By the way, if we were using a multi-threaded operating system like an RTOS, we would also have to worry about threads, having two threads that access the same variable. We are going to be looking at code shortly, and we'll be looking at the interrupt handler in some detail. To prepare for that, I want to review the UART registers and also look at some LL code related to the UART. So here's a UART register map, and you can see it has 7 registers. Over here is some LL code, and this is a structure called USART typedef that has 7 32-bit variables, and these correspond to the 7 registers in the UART. So we will be using these structures, and we will be setting up pointers such that when we access, say, SR or DR, we'll actually be accessing the corresponding registers in the UART. In the case of the status register, there are a number of bits here, bit flags, and we'll be needing to check some of those. And to do that, the LL library has a lot of hash defines that it's created, and you'll see here these correspond to those status bits. So if you look at the naming convention, it's LL, it's USART, it's the status register, and then here's the bit. And also I have some code down here which are some functions provided by LL to operate on registers, and these are specifically to disable or enable the interrupt that goes active when the UART is ready to transmit another character. And so you can see what these functions do is either clear or set a bit in the in CR1, which is control register 1, which is right up here. Now let's look at the implementation. In looking at this code, I'll skip over uninteresting stuff and a lot of the error checking code. Of course, I encourage you to read this code in detail, including all the uninteresting stuff, if you are trying to improve your knowledge of C. So we'll go through. The first thing, of course, I like to look at is the state information about the module. We keep a copy of the config. These two data fields contain the stream for the ttys and the file descriptor. This is a key variable or field. It contains a pointer to the register base of the UART. The UART registers being memory mapped. The rest of these fields are the circular buffers for the receive and transmit circular buffers. Here are the actual buffers, and up here are all of the put and get indexes. Now this module has some performance measurements, which are basically counters of different kinds of errors, and we'll see how those are set below. Let's skip through this. Now we're getting into the core APIs. Here is the one that gets the default configuration. Here is initialization. We initialize some of the state information, and one of the key things is this is where we set the UART register base address based on which instance of this module we are initializing. We choose a particular base address. These symbols here come from the LL library. If we were asked to create a stream, we create the stream. When we start the module, some of the key things are we enable two interrupt conditions within the UART, the receive character ready and the ready to transmit interrupt conditions. And then this code here is operating on the interrupt controller. So the UART has sort of a global interrupt for all of the UART if any condition is true, and we have to enable that in the interrupt controller. So now we're looking at these what I called fundamental APIs, TTY putC and TTYS getC. So put character, the objective here is to put a character on the transmit circular buffer. And there are sort of two cases. One is if the buffer is full, and the other is the buffer is not full. So if the buffer is full, which it's detecting that here, it increments a performance measurement saying I have a transmit buffer overrun, and it returns an error. This is the other case where it's not full, and in fact this is the line of code here that puts the character in the buffer. Now here is an interesting point. We turn the transmit interrupt. That interrupt, the transmit ready interrupt condition is turned on and off depending on whether there are characters in the TX buffer. If there are no characters in the TX buffer, we have to have it off, otherwise the UART will just keep interrupting us. So what we do here is, in this case, since we have just put a character into the buffer, we want to make sure that the interrupt is enabled, because that will get the character transmitted. There's one little subtlety here. Before and after this line of code, I disabled interrupts. And here's why I did that. The interrupt handler also will change the state of that enable flag. And I have to ensure, it's like a common variable that both base level code and interrupt level code are modifying. I have to make sure that that there's not any interference between those two. And so I disable interrupts while I do that. So I know that the interrupt handler is not running, and I can safely change this register value. So now we go to getting a received character, and that's a little simpler. We check if the circular buffer is empty, we return 0, there is no character. Otherwise, we get the character out of the buffer and we advance the index. So these are just the APIs to get the file descriptor and to get the stream, and that's pretty simple. So now we're ready to look at the interrupt handlers. Notice there's an interrupt handler for each of the UARTs, UART 1, 2, and 6. And the other thing you can notice is that this just looks like a regular C function. There's nothing indicating that it's an interrupt handler. And this is based on the design of the MCU we're using. It was designed specifically to make interrupts look like a C function call. With other MCUs, you sometimes have to put special keywords around here to indicate that this is an interrupt handler. In any case, all of them do the same thing. They call ttys interrupt, and they pass their module instance ID, and they pass the interrupt number, which is needed for some error case. So here is the actual work of the interrupt handler. The first statement of interest is get a pointer to the state object for this instance of the module. And then the next thing of interest is we read the status register. We take the UART register base and access the status register and store that into a local variable. So now what we need to do is figure out what caused the interrupt, might be multiple things, and handle it. So the first thing we check for is whether the UART is telling us it has an incoming character. If it does, there are two cases. One is the interrupt or the received circular buffer is full. In that case, we just increment a performance measurement saying we got an overrun. The other case, it's not full, and this line reads the data register from the UART and stores it into the buffer. And it also increments the put index. Next possible action is if the UART is telling us it's able to transmit another character. And there are two cases there. One is that the transmit buffer is empty. So in that case, we have to disable in the UART the interrupt condition of transmit buffer empty or ready to transmit. If we don't do this, the UART is just going to continually interrupt us. So we disable it. The other case is where there is a character, one or more characters in the transmit buffer. We get the next character right here and store it in the data register in the UART. And again, we have to, in that case, increment the get index. And then the final thing we check for is whether the UART is telling us that some kind of error occurred. And these errors, I believe, are all on the receive side. And we haven't really looked at serial communication in detail, so I won't try to explain what these errors are. It would be very useful for you to look into this. But interestingly enough, and this has been the way UARTs have worked, I think, all the time I've ever used them. When you get an error, you read the data register, and that clears out the error. The information that you get out of the data register, for the most part, is not useful. But this is how UARTs work, or the ones I've worked with. And then after we do that, we just go through and check each of the individual bits, and based on that bit, we increment the corresponding performance measurement. And the reason I do this is if you look at the statistics on a ttys and you're getting a lot of these errors, it means something seems to be wrong. Maybe your serial line connection is bad or whatever. So that's the interrupt handler. That one I think is quite straightforward, but I hope it gives you a flavor of what they look like. So after that, the next thing we see are the command handlers. I won't go through these. This is for the status command. This is for the test command. This test command is used for unit testing. Then the next interesting function is the _write. This is a function where we are simulating a system call, like a Linux system call, the write. And this is also a function where there is a default version of it that is declared as a weak symbol, and so we're overriding that weak version of write with our version. And it's pretty simple. We just the user passes in an array of characters, and we just go through that array, or string you could call it, and we call it ttys putc. We don't know whether it was successful or not. Maybe the buffer is full, but we just do it. I mean, there's nothing else we can do at this point. And so these characters may or may not successfully be going out. And then there's the system call for read. And that one's a little bit easier. We check if the buffer is empty. We just set the error note. We return a -1, meaning there is an error. And we set the error node to E again, which means we have nothing now, try again later. If there are characters in the receive buffer, then we put as many as we can into the user's buffer. And we return the number of characters that we have copied. So that's it for the implementation. So here we are at the console, where I want to show you a few things. First, we can see what kind of support we have on the ttys module, and we see the status command, so let's see what that gives us. Not a lot. It gives us the states of the circular buffers for the different instances. You also notice there is a ttys PM. Now this prints all of the error counts, and you can see they're all 0, which is what you would sort of expect. But what I'd like to do is sort of demonstrate a transmit overrun condition. And the way I'm going to do that is, as you might know, the question mark gives a summary of the usage for all the modules, their console commands. If I enter a bunch of question marks, one right after the next, I can overrun the transmit buffer. And of course, I've tried this just before recording this. So I am going to cut those, and I am going to paste it. And you can see that it started trying to print these, and then we get this gobbledygook, because what's happening is it's dropping a lot of characters. So that's fine. So now we can look at the PM counts, and we notice there were 1,600 cases of transmit buffer overrun. It's quite a few. So that shows you how that works. I can also do a txpm clear and tys, and it has cleared out the counts. So that gives you a little view of the console support for this module. So that's it for the ttys module. Thanks again for watching.